can help you with some more examples of variable stars. But in fact, Bia Lacertae was originally thought to be a variable star within our own galaxy. However, deep exposures revealed that Bia Lacertae is not a star but a distant elliptical galaxy. Its redshift is 0.07, puts it at a distance of around 300 megaparsecs, so closer than that first quasar. The reason why Bia Lacertae was originally mistaken for a star was that its unresolved nucleus is brighter than the diffuse fuzz of starlight surrounding it. So it's like really, really bright center and diffuse fuzz. The nuclei of Bia Lac objects are rapidly variable and have a non-thermal spectrum, but do not show any emission lines. This makes it difficult to determine the distance to a Bia Lac object unless you can manage to detect the absorption lines in the fuzz of starlight. Doing so is very difficult for many Bia Lac objects since their nuclei are so extraordinarily luminous compared to their stars. It also makes it difficult to determine their morphology. It's conjectured that all Bia Lac objects are ellipticals, but no one is totally sure. Could you please like the live? The flux from a Bia Lac object can change significantly from one night to the next. Again, that's what is true of the variable stars, right? Their flux changes a lot, constantly. So look at the live where we talked about the variable stars as well. The flux from a Bia Lac object can change significantly from one night to the next. This indicates that the bulk of the luminosity comes from a region less than 1 light day, 200 astronomical units across. So basically, if the flux is changing so much over the course of one night to the next, that means that a lot of the luminosity, again, is coming from a very point-like or very concentrated region, which could be, in this case, it is 1 light day across, which is around 200 astronomical units across. So Seyfert galaxies were first noticed because someone looked at images of spiral galaxies and said, wow, those nuclei are really bright. Bia Lac objects were first noticed because someone looked at the radio emission from Bia Lacertae and said, wow, that's way too much radio emission for Bia Lacertae to be a star. So this is kind of how the active galaxies were discovered, and that was a little bit of a tidbit from on active galaxies, particularly on quasi stars, as somebody asked, or quasars. Hopefully that was helpful. It's from this book called Foundations of Astrophysics by Barbara Ryden and Bradley M. Peterson. We talked about normal galaxies as well quite a bit, spirals, ellipticals, irregular galaxies based simply on their shapes or morphology. Now we also talked about active galaxies, where the main thing is that the galactic center of these active galaxies basically are very active, as in they are the producer of the maximum luminosity of that galaxy, and they outshine the rest of the galaxy and the rest of the stars in the galaxy by lot. And when we see them, first of all, we thought some of these could be stars. They were very star-like, and we were like, oh, what are these things? They seem to be too radio loud, because we found the radio loud quasars first. They seem to be too radio loud to be stars, but they also are very far away, and they also, you know, the luminosity is still concentrated in the center. So that's where we are like, oh, maybe these are, you know, active galactic nuclei, and we start looking, and then they had the ultraviolet X's as well. So then we start looking for more of them. We found the radio quiet ones, which happen to be most of them, and overall they belong to that active galaxies category of galaxies, which is the active galactic nucleus category, where there is a very high luminosity center doing all of the things, and pretty much a very dim blur of stars around that center, because it's not really a fully developed, substantial, normal galaxy where the stars would have similar or more luminosity contribution to the galaxy, like our galaxy does.